Okay, right, hello and welcome back to the second part of this tutorial series, Introduction to Niagara. So in part one, we had a look at some basic templates, the UI and sort of the kind of experience of building a few effects with Niagara. And in this section, we're going to do a real deep dive into all the modules. Maybe not every single one, but an awful lot of them that come with Niagara built into the engine. Now this is broken down in sort of logical sections, and so we're going to kind of, as we see here, meta properties, spawn modes, location modules, vectors and velocities, etc. And that's sort of like categorizing what the module's doing, what kind of features you're going to get, but they're not going to be full worked examples. As you can see, it's just lots of little colored dots, and so it's trying to kind of be a tutorial, be a kind of like an explanation of what's happening, but also like a reference library, so we can refer back to these later, rather than to go through a whole tutorial. If you just want to be like, oh, how does that bit work? Just refresh your memory. That's what these are kind of designed for as well. So there will be worked examples in part 4, and so that will be much more step-by-step building up an effect. But in this section, we're just going to go through. Might be a little bit dry because of that. There might be things that we only use very, very occasionally right next to things we use all the time. And so I've tried to categorize things as best we can, but it's a very complicated system. There's a lot of power and things that can be done. And so it's quite difficult to sort of build it up always in an increasing level of complexity without kind of jumping around all over the place as well. So hopefully this is helpful. This is how I like to sort of understand things. As I say, if you prefer more of the sort of worked examples, they will be coming later on, and there'll be more tutorials and more examples later on in the future as well. So yeah, module by module, break down sort of properties, what's happening, how do we do it, what settings do we have, and we'll cover all of this, and we'll start with the emitter properties in the next video. Okay, so emitter properties. Well, if we open up our system here, we can see we have just an empty we started with, and we're just going to sort of go through, add, take away, turn things on and off, and kind of like really isolate the different settings and what's happening. So this one, we're going to be talking about this module here, emitter properties. Now this is inbuilt. We're not able to remove it. It always exists, and it gives us some overview or overarching settings that we can do to change how our emitter works. Have a quick comment down the side here, sort of partly to remind me what's there, but also it's just a sort of a quick sort of summary. But obviously we're going to go into much more detail here in our sort of discussion. So emitter properties, starting with the first one here, local space. So this is an option for whether we're storing our particle information in world space or local space. So just as a quick kind of demonstration of what that means, if I create a cube, and I move it over here so we can see what's going on. If I were to rotate this 45 degrees or 30 degrees or whatever it is, I'm still moving this in world space. You can see my axis, the direction of the axis is always aligned with the world. So it's aligned with this gizmo down here in the bottom left. That means that we're moving it in world space. That's the coordinate system we're using. If we click this little icon at the top here, we can transform or change our gizmo coordinate system between local space and world space. And so now, if I rotate my cube, you'll see the x-axis of my cube is always sort of facing along the angle of the cube. So that's what we mean by coordinate system. There are many. Local and world are two of them. There's mesh coordinate system, there's particle space, there's screen space, there's world space, there's clip space, there's all these things. All they are is just coordinate systems. Where is 0, 0, 0? Where's our origin? And which direction do our axes move in? And that sort of defines a space. You will notice, or you might notice, even though this is in local space and we're moving, these numbers here are in world space. Oh, let's just make my UI a little bigger. Little trick, if you are recording video or things like this, you can open the widget reflector in debug and just scale your application, which is quite a nice little thing. Try and remember to do that before we do recordings. There we are. Now we can see this a little better. The movement is happening in local space because that's convenient for us, but the data is being stored in world space. And so you can always convert from one space to another, and there's some transforms and inbuilt nodes to help us do that. So yeah, so that's what spaces are, that's how they work. What does that mean in terms of our particle system? Well, if I move this over here, you can see over time new particles are spawned, old particles die. The particles are being stored or being calculated and saved in world space. Very useful. If we're moving something along, we want a trail, that's great. What happens if our particle effect was some kind of, like, I don't know, magical bracelet, ring, thing like that was attached to a character bone? Whenever I move my object, I'd like the whole system to move with it, all the particles. And that's what this does. So if I enable local space, now these particles will just move with the emitter. Very useful. When you want it on, you want it on. When you want it off, you want it off. It's usually pretty obvious. But generally, personally, if I'm dealing with something that never moves, it doesn't really matter whether it's in local space or world space. But if it's something like a fire, like a static campfire in the world, it's much easier to place if local space is on. So I tend to work with local space on and turn it off when I need to. You could see, hopefully, if this was just a campfire. I think we do have a campfire. Let's see if I live up to my example. There are. If I move this around, it's much easier to just kind of place this into position. If this wasn't in local space, you'd have to kind of wait a few seconds each time for the particles to kind of get to the right place and stuff like that. So it doesn't make a real big difference when we're dealing with static placed effects. And so personally, I think, well, just have local space on. It's easier to place things. But obviously, if it's some kind of trail, some kind of attachment, it's going to make a big difference whether it's local or world. Okay, cool. That is a good place to stop for this video. In the next one, we'll have a look at determinism and whether how that works with our emitters. Okay, right, let's have a look at determinism. Next option on here. If I disable this, turn it back to the default and have that off, if I look at my particles, every time my particles reset, they're going to reset completely differently. We're going to get a new arrangement of particles spawning. They're all doing the same thing. So they're spawning within a sphere, they're spawning at a certain rate, and we'll cover those modules in a bit. But if I look, this particle up here that's kind of isolated on this iteration, if I reset, it's, well, maybe we get another one. Oh, it's not quite so isolated. They're different each time. Each time it's randomizing completely everything. It's not using any kind of data to seed its randomness. And that's what determinism does. If I enable this and then have a look, and let's have a look. This arrangement here with 3 particles that spawns in very quickly, every time does the same thing. So it's deterministic. Basically, we're using a source value to calculate our random value. And so whatever our source value is, it's going to continue that, and it's going to be random each time. So one thing I like to kind of bring up as an example for this, before we had computers and calculators, random number table, people who wanted to do calculations with randomness, mathematicians from sort of, I don't know, Middle Ages, they would buy books of random numbers. You would just buy a book, and it's time you would just kind of say, right, I'm going to start with a random number here, this page, this paragraph, this chapter, this digit, and then the next number is going to be completely independent from that, and that's therefore random, and you can go on and go on. But every time you look at the same digit, the same page, it's always going to be the same thing. And that's kind of the idea of seeded random. Each individual sort of lookup is independent from the previous one, but if you put the same data in, you get the same data out, as if it was just a book of random numbers, not just a purely randomly generated number. So that's what the next thing is here, random seed. If I change the seed value, let's say 5, I'm going to get a different randomness, but it's going to be the same randomness every time I plug in 5. It's a very common thing to use in randomness, whether you do seeded or unseeded random, and they have pros and cons. If this was just a gameplay effect, you'd want it to be different every time. You'd probably want determinism to be off. If it's a cinematic effect, it's part of a game trailer or a cutscene, you probably want it to be the same every time. There's nothing worse than if you've got a cinematic effect, and let's say it's some leaves falling or something like that, and you do your final render, you're really happy with everything, and then all of a sudden at some point a massive leaf just comes across the screen and across the camera. Obviously randomly that could happen, so good idea to use determinism in your cinematics. But obviously if we have it on for every gameplay effect, well, now we'll start seeing repeats, we'll start seeing the same thing every time, it won't look so good. So that's what this setting is for here. So one thing also with this, if I turn it off and then I look at my timeline, I can move forwards and I can pause, just click and drag here on the little time marker. But if I tag backwards in time, it doesn't really work. It doesn't go forwards and backwards, it struggles. And you can kind of see particles spawning and then just this kind of flickering, because that's the way the particle system's working, is it's calculating the next frame based on the previous frame. So we're always able to move forwards in time, but there's no support for moving backwards. If I put determinism on, now if I scrub back and forth, you can see that the particle is able to kind of like go back in time, but because it's based on the same seed and the same randomness, it can calculate forwards every time. So if I click on 3 seconds, it hasn't taken away half a second. Instead, it's recalculated from the start forwards 3 seconds, but the result's always the same. So if I go like this, it looks like I'm going back and forwards in time, which it sort of theoretically kind of is, but actually I'm recalculating from the start each time, but I'm just always reaching the same result. Hopefully that makes sense. It's a bit confusing, but yeah, that's what determinism's doing. That's the difference, seeded random versus unseeded random. You'll see this kind of thing very common. Lots of software, whenever there's kind of any generation, often gives you a random seed to allow you to quickly change that value. As I say, useful for cinematics. I've heard recently of people who use it on while they're making an effect, so they can do this kind of scrubbing and pausing, and then at the end they just turn it off again to make it sort of reusable in gameplay, which isn't a bad workflow. I quite like that as an idea. So yeah, determinism and seeded random. In the next video we'll talk about interpolated spawning. Okay, right, interpolated spawning, what does that mean? Well, let's just keep determinism off for now. So when a particle spawns, it will run through the particle spawn section, this simulation stage, or this module block, whatever we want to call it, and then it will carry on. It will just say, right, that's me, I've done my spawn bit. What's next? Well, the next frame, it will say, now it's time to update. I will run through my update, and that's fine some of the time. But sometimes, let's say we're spawning our particle and they're this size, and let's just get that playing again. So we're spawning particles that are a fixed size. It's not very good. Let's use a curve, and if I do scale sprite size and just do a uniform curve, I'm now spawning my particles, scaling their size to 0 and scaling them up. That should work nicely, but there's a problem. You see this horrible flickering. Well, what's happening is the particle spawn is calculating, this is being run, and then there's a pause, and then the next frame, the update is run. So this scaling down to 0 only happens 1 frame after being spawned. Sometimes that's fine. If so, we can keep the interpolated spawning off. But if you are getting this kind of problem, by turning interpolated spawning on, it will now, on spawn, on that very first frame, not only do all the spawn calculations, it will also do all of the update calculations. And so you're getting kind of like a first frame run through of your update script. It does add additional cost. It says adds significant additional cost here for spawning, and so if you can avoid it, then obviously do, but there are definitely situations when you can't avoid it, and so it's nice to have that option. In this case, you could start with, I don't know, maybe setting the initial size to be very small, and then your scale to be very, very big. And you've kind of done the same thing. Oops, that's maybe too big. So now you've kind of worked around it, started with a very small, you don't see the pop, and scale in. That might work. It's a bit of a hacky way of working. If it's not just size you're dealing with, it's a bit more complicated. And so having this option to turn on interpolated spawning just means that it will run your script but no, there is an additional cost to that as well. So if I set that back, set my size back to 10, and then fix it with interpolate spawning instead. Here we are. Cool. Okay, that's interpolate spawning. Let's say use it when it is required. I think the default is off because of that performance reason, but yeah, do be aware of it's adding a cost. But again, it fixes the problem, then it's probably worth using. Okay, in the next one we'll talk about sim targets. Okay, right, so the next part we're going to look at is simulation target, or sim target here. Now this is one of the most important things. Maybe we should have started it, but we're going through the list sort of top to bottom. And this is what part of our hardware is doing the calculation. So by default, it's set to CPU simulation. So the CPU is doing the calculations for everything here in the particle. Or we can change it to be a GPU simulation. And now our GPU is doing the calculations for us. So why might we want to use one or the other? Well, there are lots of reasons. Depending on what you're doing, well, for a start, there are some things that are only possible on one or the other. When we look at collisions, we'll look at what's available to the CPU and what's available to the GPU. There are certain features, such as reading textures, that are only available on the GPU. And so, depending on what simulation type you're doing, you have a slightly different tool set. And so when it's appropriate to use one on the other, we'll cover that, and we'll talk about that when that comes up. Partly it's for performance. If your game is CPU bound, if your CPU is the thing that's working at the maximum level, then no amount of optimizing on the GPU is going to make any difference to that. And so if you're really at that fine tuning level, you might find that it's easier to move some of the simulations from one sort of target to the other to free up resources on the other. And that is a good way of optimizing. But generally these days, the GPU is much more designed, it's much more built around doing large amounts of sort of parallel calculations, and that's kind of what you need for a particle system. So most particle systems these days are going to kind of want to be GPU simulations by default, but there definitely are reasons not to do that. If we're talking about VR and mobile hardware, they can be very, very different things. Obviously, some mobiles don't even have a GPU, and so therefore we're limited with CPU, some simulations as well. So that's kind of why there's an option for both. As a quick sort of demonstration, if I go to my CPU sim and spawn rate, and we're just going to spawn a crazy amount of particles here. So I think it's 100,000 particles a second. This is going to tank my frame rate. Hopefully that comes through in the video. My frames have now dropped to about 15, 16, 18 frames a second from the 30 I was getting before. And so dedicating a lot of extra performance to deal with these 100,000 particles a second. I think it evens out at about 250,000 particles, maybe a bit more. What's that, 500,000 particles? Which is a lot. This is a terrible way to make a white glowing sphere, but hopefully a decent demonstration of the difference between a GPU and a CPU sim. So 500,000 particles costing us about 12, 13, maybe 10 frames a second in performance. Obviously that's all very dependent on what your hardware is, etc. But if I change this now to a GPU sim, give it a second to compile, and there we are. My frame rate's back up. We've got now still 500,000 particles, but if I go in and I change my 1 here to a 5, we can spawn 5 times the amount, and we're looking at 2 million particles. I mean, it's still tanking my frame rate. Point being, you can have a lot more GPU particles. There are certain effects, especially if it's like cinematics, or if you're using Unreal for something like motion graphics, you're going to want lots of tiny little dots swirling around. That's completely unfeasible with CPU. With a GPU, GPU simulation, you can deal with those kinds of numbers and calculations. So obviously it depends on what you're making. Thankfully, a lot of effects we have in games don't need millions and millions of particles, but there is a big difference in the performance costs between CPU and GPU. So having lots and lots of tiny things is much more sort of GPU focused, whereas having fewer more complicated things might be more sort of CPU. But as I say, we'll cover what features are available to us on which platform. It's not like there's a right and wrong answer. It depends what tool set you want to use, what feature set you want to use, which one is the correct thing to do. But as a sort of general rule of thumb for modern console game type projects, you're probably going to want to do most things on the GPU, and you're going to get better results with that. Okay, so the last or next sort of setting on the list is to do with the bounds. If I set this to CPU, we can have dynamic bounds. It says it here, only available for CPU emitters. What does this mean? Well, if I go in here and enable bounds in the view, show advanced bounds, every object in Unreal has its bounds, has a box surrounding it that tells you how big it is. That bounds is used to do a calculation. Let me just have less spawn rate, that's crazy. Your bounds are used to do your visibility calculations. So the first thing the engine will do will work out if the thing that you're talking about, in this case it's a particle system, if the actor is in screen, and it will do that by calculating the bounds and then saying, right, is that something I should render? If it is, then it'll sort of load up the meshes, load up the sprites, textures, etc. So the bounds calculation is done on a very simple box to be very quick and efficient, and every object has a bounds. Well, that's turned off again. And there we are. If we select it, we can see this box surrounding it. Now, if I reset my simulation, you can maybe see the bounds is updating. So as the object changes, as the particles get more and more, it sort of fills in that shape. Now, this is being done on the CPU. So the CPU knows where the particles are, and therefore it can refer that information back to the bound system to say, well, this is how big a box I need to make sure I encompass all of the particles. That's great, no problem with that. But that's not possible with a CPU simulation, with the GPU simulation. With the GPU sim, all of the information needs to be sent from the CPU to the GPU. There's no backtalk. You can't take information from the GPU back to the CPU. And so it can't have dynamic bounds. It doesn't know. And if we have a look, the bounds now has just gone to a default size, and we should be able to break it. Well, let's set my bounds to be something smaller so we can do a fixed bounds. If I set my fixed bounds here to be just a really tiny box, just 5 units across, we can see, don't know if we can see, but there's a tiny little box in here. And if I move the camera off the side of the screen, as soon as that little box disappears, the whole system disappears. Or the whole emitter, I should say, I guess, because it's per emitter. So that's what the fixed bounds is doing. We need to tell it how big a box is the system ever going to be, and anything that's outside of that has a chance to be accidentally culled. As so there is a limitation to using GPU simulations. We can also do fixed bounds on a CPU sim, and it will be a slight optimization. And so you might find that there's fixed bounds set for a CPU sim, because then it doesn't need to do the calculations, it just knows what the number is. You can also use programmable things. I've not done this myself, but you can set scripts to then program how big the bounds is going to be. It's a bit more advanced. Yeah. One nice little tool. We've got bounds up here as a visibility thing. We can turn on the bounds. And if we click at the little kind of 3 dots icon next to it, we can actually set our fixed bounds from our system. And so if I do here, set fixed bounds emitters, what that will do will calculate the numbers for us for this box. So once you've done your calculations, done your system, set the fixed bounds if you're using fixed bounds, and then I usually just come in and give it a little bit of extra. So you can see here we're about 100, and so let's give it just a little bit, 125, maybe 150. Partly I like nice round numbers, it's easier to understand that, and it just gives us that little bit of extra detail. So you can see here when I do the set fixed bounds, it's obviously taking the exact positions of the particles at the moment. If we do a GPU sim, it'll do the same. And so there might be a particle that could potentially spawn outside of these bounds, and that's why we're getting the sort of the small variation in the numbers. We could work it out. In this case, we've got a sphere with a radius of 100. That's our shape location. So we shouldn't really be able to get particles outside of a bounds of 100. But I mean, I guess there's some inaccuracy somewhere. But a little bit of extra, just give it what I would call a factor of safety. A little bit of sort of, yeah, extra just in case. And now we have a nice fixed bound for our simulation. On CPU, as an optimization, on a GPU, it's kind of required. And you do get a warning about that as well. So here, the GPU is, the emitter is GPU, and it's using dynamic bounds. Please update. And so we can change this to be fixed. And there we are. Okay, that is it for CPU and GPU simulations. As I say, by default, you probably want to err on the side of GPU. There will be certain features that are only limited to CPU. And also some that are only limited to GPU, and they'll come up when we talk about them. But yeah, a big difference between what's happening. Okay, last thing on his list is requires persistent IDs, and we'll cover that in the next video. Okay, right. So the last setting in here that we're going to have a look at is requires persistent IDs. So by default, when particles are spawned, they're assigned an ID, and that is useful for various calculations and everything, and sort of storing and tracking that particle. But as that particle dies, that ID number can be reused and things can change under the hood to be nice and optimized, so we're not storing excess data that we don't need. That is fine, but certain things that we will do will require persistent IDs. And when we need that, that's what this option does here. So it creates a stable value that does not vary from frame to frame at a small performance and memory cost. Not something you want to turn on when you don't need it, but when you do need it, obviously it's required, and that's where the setting is for that. And we'll see when that comes up, what we're doing that requires persistent IDs, and how to enable it there. Okay. Last thing we have on the emitter properties is this big plus stage button. So we can add additional stages to our system or to our emitter. We'll be covering the event handler. That's in the next module when we look at advanced concepts and how that works, and we can send information and events from system to system or emitter to emitter. And we'll cover that one. And then we also have generic simulation stages. And so this is where we can get into really complex and advanced things, where basically we can write our own simulation stage. What do we want to happen using a grid 2D or a grid 3D or any kind of thing we want. And we'll be doing some future tutorials on simulation stages. So I'm not going to be covering sim stages in this section just because it's an introduction. Instead, I'm going to do a deep dive into grid 2D as its own kind of separate course at a later date. So that's what these are. As I say, we'll cover event handlers. We won't really cover simulation stages. It's very advanced, but that's how you would add them if you needed to. And that's that button there. So that's all of the emitter properties. As I say, it's a module you can't remove. It's not really a module, I guess. It's just some settings, but overarching parameters that are affecting the whole system or the whole emitter. Yeah. Most of the time you go in there once, you turn them on and off, you set them up, maybe at the start of your sort of particle work if it's something like local space, maybe at the end if it's something like bounds, but we're not going to spend loads of times in here. It's just nice to know there's some settings. Where do they live? Okay, they probably live in the emitter properties. Worth going in and checking. Cool. All right, in the next video we will have a look at something a bit more particle based, and that will be the spawn modules. So how can we add particles to our emitters? Used a couple of these already, but we'll just go into a bit more depth with the spawn modules, and we'll do that in the next video. Right, okay, so actually, tell a lie in the last video, we are not going to move on just yet. We've been looking at the emitter properties and going through what they are and how they work, but we also have the system properties. So just quickly, a lot of these are the same, but can be set for the whole system, as I said, as opposed to just sort of per emitter. So determinism, we covered that. That will be the same, but now affecting everything. So this setting overwrites these settings here. And I think, in fact, if I turn that on, it may even It doesn't. Okay, fine. But we can set that sort of for the whole system as opposed to the emitter, just sort of a more convenient way of working. Similarly, with the fixed bounds, you might have seen before, we can do set fixed bound systems and emitters. If I turn this fixed bounds on here, that will be now the fixed bound for the whole system, rather than doing it per emitter. So that's another option we have here. There's a few rendering flags. Do we want to cast shadows? Do you want to receive decals? Do you want to render to custom depth? These are all just options we can quickly turn on and off. And then a few other things. We have here effect types, where you can set an effect type. This is to do with optimization and scalability, and allows us to sort of set our kind of our settings for the type of effect that we're dealing with. Is it a gameplay effect? Is it a background effect? Is it a weapon muzzle flash? That kind of thing. Sort of an importance hierarchy, and then control that. And we'll go into template effects, or sorry, effect types in more detail in a separate video later on. We have an option to tick fixed delta time. So by default, the particle system is ticking at the same rate as the game is able to tick. So if you have a very expensive frame, there's lots of other calculations happening, you'll have a very sort of long time between your particle ticks and particle updates. It's not really a problem. Usually you can calculate your kind of velocity based on your tick rate, and so kind of your velocity will sort of smooth out naturally by the way the calculations are done. But sometimes it can cause problems, and so you can set a fixed delta time and say, I only want you to update, or I want you to always update at this time here. And says, note this forces the game to tick on the game thread instead of asynchronously in parallel. So if you're dealing with something that's sort of, I don't know, requires something very stable, so something maybe physicsy, or not sure where exactly you'd need this to be enabled, but you have this option here. So you could sort of say, I want this to always update everything. It's going to be stable, but obviously it's going to come at an additional cost as a different way of doing it. Warm-up time. This is always a fun one. If I head over to my viewport and hit my reset button, you see it takes a few times, a few frames, a few seconds to get particles into my sphere. Sometimes that's fine, but sometimes it's not. Sometimes we want this to appear immediately. As so, we can set a warm-up time. So if I set 1 second warm-up time, what it will do in that very first frame, when it requires the particle to be drawn, it will run a full second. In this case, it's 14 ticks worth of update off screen before it spawns them on the screen. This fixes that problem, no problem, nice and easily. Let's put this up to something like, I don't know, 5 seconds. Great. There's a really big performance impact to this. If you think about it, it's trying to do lots of calculations every second, trying to do 47 times that calculation. In this case, it's a very simple system, very simple emitter. We're not causing any real problems. But if this is anything more complicated and we're trying to do 74 times the update that we should always be doing once per frame, you can see how that's quite a big number. There's a lot more calculations going to be happening. You're going to get stuttering and hitching. Not really what you want. So that's what warm-up does. Just be aware that it can cause some quite big performance issues in itself. Generally, games don't worry about it. I'm sure you've all played a game where you load in and you load a new scene, and then all of a sudden the world kind of appears and slowly just sort of fills itself with particles. That generally is acceptable to most players, but if it's really not and you've got the performance, you can set some warm-up time values in here. So tick through 10 frames off screen, and then suddenly now they're there. Okay, talking about performance, a couple more options here. Requires current frame data. So do we need some information from elsewhere in the engine? If so, then we need to have this enabled. If not, then we can turn this off, and now it will fit the sort of particle simulation calculations in where it can, where necessary. It allows it to be a little bit faster, but if there are any dependencies, you might have now gaps. So you're able to deal with sort of, I don't know, something like collisions. You may need the current frame data to do the collisions accurately, and so that would need to be enabled. if you were dealing with sort of, I don't know, some kind of huge destructive effects, that kind of thing, or some gameplay sort of focused things. Not entirely sure, but if you need the current frame data, that would need to be enabled there. But if you don't need the current frame data, you can kind of disable that and have a little bit of performance back at the cost of potentially creating gaps or visual artifacts. So something that's attached to a character, that character is moving, you need the current frame data to know what the character is. If it's just sat in the world not doing anything, well, maybe we can just get away with having that turned off. Last option, auto deactivate. Do we want to have the particle system to deactivate itself when there are no more particles? So if you have a kind of a spawn rate, or if you have a burst of particles spawn as they slowly die, it will then just deactivate the particle at the end of its lifespan. So generally wants to be enabled. For something like a looping effect, well, we never run out of particles anyway, so it's fine. But for a burst effect, we want this to be on as an option. Okay, that's the system parameters, system properties that go with the emitter properties. Obviously a few duplicated just for convenience, and then a few kind of specific ones. And we'll, as I say, cover effect types in more detail later on. But now we are going to move on to the next one, spawn modules, in the next video. Okay, right, so in this next section we'll be having a look at the different spawn modules. As I say, we've used a couple of these already in the examples we did in the first part, but we're going to go through these in a little bit more depth, and there's a few we haven't used yet. So yeah, spawn modules. So they live in emitter update. So every frame that the emitter is live, it's saying how many particles should I spawn, or should I spawn particles at all, or how should I spawn them. And the most obvious one, or the most sort of basic one, is the spawn rate. How many particles per second? Larger numbers will be more particles. We get a live preview up here of how many particles are currently available or currently alive. Same up here as well, 2,500, 2,500. And yeah, very common for any kind of ambient effect, whether that's sort of weathery, sort of snow, rain, etc., or fire or whatever. We're just going to want a number of particles over time, and we can do that with our spawn rate. We also have a spawn probability, and so this is not quite like a multiplier. This tells the system, or tells the spawn module, should I spawn on this frame or not? And so if I put this down to 50% probability, we're kind of getting the same as a spawn rate of 25, but rather than being a consistent 25 particles a second spawn rate, it's sort of intermittent. And so every frame has a 50% chance to spawn or not. If it does spawn, it spawns at a rate of 50, but if it doesn't spawn, obviously that's 0. And so it's kind of like a way of breaking up that natural sort of that uniformity, that consistency, and making it feel a bit more natural. I'll worry about spawn group for now. Yeah, we can of course use curves for these things. So if our spawn rate was set to float from curve, because we're doing a curve in the emitter update section, the curve index, or sort of what's the x-axis effectively, is set to the normalized loop age of the emitter. What does that mean? Well, if I go to our emitter state, this is currently being driven by the system. So to go to system state, our loop duration is 5 seconds long. So this graph here is 5 seconds long, and we can kind of control our spawn rate over that 5 seconds. So by doing it by the normalized loop age, it kind of scales depending on what the loop setting is, if that makes sense. So if we spawn here to start with a value of say 50, and we scale down to a value, let's do that in the curve, shall we? So at keyframe of 0, a value of 50. No, let's do the other way. So let's keep our keyframe values 0 to 1, and we'll do a scale value of, let's say, 50. So it's now 50 particles a second to start with, and then over 5 seconds, they're going to start dropping off. And if I make my lifetime a lot lower, maybe we can see this a bit better. Let's this up for a second. Let's move it the other way. So if we set our lifetime loop duration, let's do something really big like 50 seconds. And so our spawn rate starts at 0, and over 50 seconds it's going to go up to 50. And so we can get this kind of build up and culmination. Let's do our loop duration, let's do it 10 seconds so it matches here. Makes more sense. There we go. And hopefully you can see that's working that way. So at 0 seconds in our emitter loop, our spawn rate here is 0 times 50. And then at 1, which is the full length of our emitter loop, which is currently set to 10 seconds. So here, our spawn rate goes up to, in this case, 50. So you can control your spawn rate over time as well. Generally, single value, how many particles do we want per second? That's going to do a lot for most sort of ambient looping effects, but we can go a little bit deeper, control it with a curve, or introduce some spawn probability. If we set this down very low and this one very high, then occasionally we'll get kind of little bursts of lots of particles, because when it does trigger the probability, let's say, what's that, a fifth of the frames, when it does, it's going to spawn lots, and so we get this kind of like staccato bursting, and all that's doing is just changing these values here in the spawn rate. Obviously, if we change our lifetimes, that's going to affect things as well. So we can get these kind of like really intermittent spawning. So spawn rate not just for constant value, but obviously you can adjust it and edit the values, different inputs, to create these kind of more random staccato type effects as well. Cool, that's it for spawn rate. In the next video, we'll have a look at spawn burst. Okay, so enough spawn rate. Just using the enable and disable modules here to step through these, make it nice and clear what's there and how everything's visible and what have you. So spawn burst instantaneous. We used this already as well, but basically it's a number and a time, and that's it. So here we are getting 10 particles on frame 0. Fantastic. If we put this to, let's say, I don't know, 1 second, we'll reset and then wait a second and then it'll spawn. Nice. We can have a number of these. So if you wanted kind of like a double, Control D doesn't duplicate the module, sadly. Control C, Control V does, or copy paste at least. So we can have 10 there and then 10 a second later, and now we'll get kind of like a double burst at the start. No problem with that. Obviously probability works as well. So if we have a 50% probability of each one of these, there is a 25% probability, 0.25, to get both, 0.25 to get neither, and 50-50 you'll get one or the other. There we go, got both. Got the second one, got just the second one, got both, just the first one. Try and get a neither. There we go, neither. So there we are. You can put probabilities in. You can choose whether you want to burst. Again, if you're doing big explosions, you want to create variation. Having trails of sparks that may come off at a low probability, or other ones that come off at high probability, will help break up that repetition. Very nice way of working. And especially with like explosions, quite often you have an initial burst and then a secondary burst. So you're like, one explosion, or the initial explosion will blow fuel up into the air, and then the second explosion will happen when the fuel catches fire, and you get this boom boom type effect. Very easy to do with setting our spawn time. And we have this option here, loop count limit. Currently our emitter is set to a infinite loop duration, or a 10-second long infinite loop. We can do a multiple, let's say a fixed number of loops. So we'll say I want to do 3 loops, and then it just stops, and we'll make each loop, I don't know, 2 seconds long. So the whole thing is now 6 seconds. And if we have a look, I might just delete this one for now. We're going to get a 10 particle at time 0 in each of our loops. 1, 2. Obviously the preview kicks in as well. But we can sort of adjust that. We can say, right, I want to loop 3 times. Each time I loop, each time I'm at time 0, spawn these. But we could add a loop count limit. So we could say, right, only spawn on the first loop. And there we are. Obviously, it's resetting once the loop is hit. So quite a nice way of working, a nice way of controlling things if you need that. Can't think of many examples where you would really need that, but it's nice to have that option in there for you. And that's what that sort of setting does, the loop count limit. How many times do we want this loop to happen? So the first one, usually it's going to be the first one, but sometimes it might be want the first 2 or 3 out of many. And you can control that by changing your loop settings here and changing your burst settings here. While we're here, if I change this back to an infinite loop, and I'll set this back to be just, there we go, probability, that's why it wasn't every time. So we're getting 10 particles every loop. And let's do this back to where it was, just to demonstrate that properly without the probability messing it up. So I'm having 3 loops of a second, 1, 2, 3, every time it works, and then it resets. It's a bit clearer. And if I set my loop limit to 1, now I'm going to get 1, and then no more. There we go. And so we could set 2 out of 3, and you could do that kind of thing. What I was going to say, currently our looping is happening. If I set that back to infinite, our loop duration is always 1 second long, and so we're always getting this very kind of repetitive burst, particles, which might be fine. That might be what we want, but if we want to create some variation in that, we can calculate recalculate our duration of our loop. And so if we now make this a loop duration random range float, and we'll do between 1 and 2 seconds. So sometimes we get a 1 second loop, sometimes we get a 2 second loop, and that just helps to spread out those bursts. And because we're recalculating every loop, sometimes it's a long one, sometimes it's a short one. If I put this in really quite small, we can now see we're going to get, despite the same spawn burst, say 10 particles every time we loop, because our loops are sometimes long and sometimes short, we can create kind of like an intermittent bursting effect just by adjusting their settings, which is quite nice. Another little trick with this, if I make another one of these, let's say we have a really big burst, but our big burst only happens when our sort of in the higher ends of our loop time, if that makes sense. So if I set my big burst to only happen at 0.8, some of my loops won't have that big burst, and occasionally they will. And so we're creating quite a lot of randomness and interaction between our simple bursts, this number of particles at this number of frame, or this time, and our loop. Sometimes our loops are quick and we don't hit the big burst, sometimes our loops are slow or long and we do hit the big bursts, and we can see quite a natural pattern here, breaking that up, even though we haven't actually done anything like, say, randomize the spawn. Obviously, we can just do a random amount. Do we always want 50? Well, no. Sometimes we want 35. Sometimes we want, let's say, 200. And now we're going to get occasional huge bursts of particles, but usually not that many, and so on. And we're going to kind of build up these kind of layers of randomness. As always, the more randomness we can add, the more it sort of feels dynamic and natural. Unless we're doing something mechanical or electronic, and then we might want to have 10 particles every second, very much kind of like on the dot. But yeah, nice way of working, changing the spawn values here, spawn time, and then the loop times, to create kind of interactions and patterns between them that are very hard to predict. Cool. Hopefully that will make sense. In the next section, we'll have a look at spawn per unit and see what we can do with that. Okay, spawn per unit. So if I enable this, and I'll just, this will set to default, this will not add any particles to the scene. What it does is it adds a particle every time we move over the certain threshold, which is our spawn spacing. So as I move my particle here, or I move my system, every time I move 20 units, it adds a particle. So if I put this number down, let's say every 5, now we're going to spawn lots of particles. Now this is really useful for trails. So any kind of effect that's attached to a moving object. Perfect example would be something like a car exhaust. The faster you move, the more particles you want to spawn. If you just don't have a constant spawn rate, well, when you're not moving, you might have too many particles on top of each other. That can cause performance issues. Or when you're moving really fast, you might have big gaps between your particles because your spawn rate isn't fast enough to deal with the sort of the speed that the object's moving. So one way to deal with that would be to use your engine or your car vehicle speed as your spawn rate and sort of scale those two things together. That would totally work. And you might do that as well. But also we can have a spawn per unit module here as well. So the faster we move, the more we spawn, but it's always kind of consistent because it's based on the distance traveled rather than any kind of like time-based thing. So really powerful, really useful. Generally you want to have it with other spawning as well. So in the case of the exhaust, you'd have kind of like a default amount that was always spawning and then a spawn per unit amount that was extra when you were moving. And so you don't get this effect where we have here where there's nothing visible because we're completely static, and then suddenly we move and we get something, unless of course that's the effect that you're trying to build. Cool. Maximum value threshold here. There are times when you kind of move an actor very, very far across a level. You might teleport something. It's maybe a start of a cutscene. Your character was in this position during gameplay, and then the cutscene starts and they move over there. Well, the engine reads that as a very big movement, and what you probably don't want is a big trail of exhaust behind you. So you could disable and re-enable the emitter. That would be fine. Or you can just have a maximum threshold and it'll say, okay, you've moved over, in this case, 5,000 units. That's probably not something I want to create a trail for. That's probably a teleport or something else that's happening. So that can help fix some errors where you get a huge movement all at once. And I can just about trigger that by moving my mouse far away, kind of across the screen. So that's what that does. Movement tolerance as well. So the same kind of limit, but the other way around. And so you can say, I want this to only spawn particles over a certain threshold. So if I set my spacing to say 20, and my tolerance to say 5, is that going to work? If I turn off my grid snap, little movements don't spawn anything, but bigger movements do. And there we are. You can see how I'm able to kind of like create that, but just a little kind of idling. If there's a little idling animation, it wouldn't create any trail, and that's because of this movement tolerance. Now it is creating one every time. And then spawn probability. So we've seen that as well. On that particular frame, is this active or is it not active? If it is active, do what it says. If it's not, then spawn them. If it's not, don't spawn anything. Okay. Yeah, spawn per unit, again, very, very handy when we're dealing with moving characters, moving effects. Having once worked on a cutscene where a vehicle moved a different speed in every single cutscene and the engine didn't have spawn per unit, so you had to make a different particle effect for every scene in the cutscene, which was awkward. Obviously it was fine, it worked, but a lot more data to manage, much easier if you can just plug in some values and just have it work. So yeah, spawn per unit. One thing to note, it does struggle sometimes with very fast movements. If we set this up to just a really small amount, we can't get any more than this, as it were. And so there are some adjustments you can make to this. I think we'll be looking at that in the next course, in the advanced Niagara, actually going in and making some adjustments to the spawn per unit module to deal with very fast frame movements and kind of sub-stepping and that kind of thing. But yeah, look out for that in the next course. Okay, in the next video we'll have a look at spawn per frame and spawning particles from other emitters. Okay, so just a quick look at these last two. spawn per frame does what it says. How many particles do I want every frame? This is a new experimental module. It has some potential issues. Basically, it's doing the same as a spawn rate, but rather than being time dependent, it's now frame rate dependent. So if our frame rate got higher, we would spawn more particles. There are limited uses for this, but if you do need it, obviously it's useful to have it here. It does come with a warning that this is frame rate dependent. So if you used this and then someone had a very good hardware, they might get a lot more particles. And if you used it on someone who didn't have very good hardware, they might get less good or less amounts of particles. Fewer, I should say, really. But that's not a very good way of working. We don't really want more or less. We kind of want it to be consistent, which is why we tend to use spawn rates. But there is obviously an option in here for spawn per frame as well. Spawn rate, or sorry, frame rate and time in seconds, obviously connected based on your sort of hardware and what's currently happening in the game. So yeah, spawn per frame, it's here. I would not use it very often. I don't think I've ever used it, but it exists and is there. And then the last one here, spawn particles from other emitter. We're not going to cover this now. We need other emitters to do this. Instead, we'll cover it later when we do the next module, where we're going to have a look at using the particle attribute reader, which is what this is doing. So you're able to spawn off one particle, fire it through the world, and then use that as a source for another particle, and that's what this does. So, but we'll go through the settings to do with that when we actually get to the attribute reader in the next section. Okay, that's it for spawn modules. You can do spawn from vertex painting tool or vertex animation tools. That's far too advanced for an introductory thing, so we're not going to be covering that one. But the 5 main ones here we've looked at: rate per second, burst number at a time, per unit is per unreal unit per movement, per frame is a sort of alternative to rate, but probably not to be used very much unless there's a specific reason you're doing it that way. And then particles from other emitter. We'll do that when we cover it in attribute. Oh, there's also spawn particles in grid, and again we'll cover that later on as well. So you can specify a grid location and then a number of particles and spawn particles in grid, but we'll have a look at that in the grid location module, which I believe is the next one. So yeah, next videos or next section, location modules. Let's just fix that, get rid of you. There we are. So yeah, obviously a big part of how our effects are going to look, how we're adding particles, what we're doing. Lots of variation. Try and break it up as much as possible, but it very much depends on what we're trying to create, whether we want to use a constant spawn rate, a variable spawn rate, an animated spawn rate, some bursts, constant bursts, intermittent bursts, random bursts, all of those things. And there's a lot to be said for combining things as well. If you've got a light and it's sparking and it's firing out sparks constantly, but that's sort of animating, and then occasionally there's a big burst of sparks and all of those kinds of things, help to add that sort of level of realism and dynamism. So no problem in using 2 or 3 of these modules sort of at the same time. It's not just a case of either spawn rate or spawn burst. You might want to have a baseline spawn rate, an animated spawn rate, a spawn burst, another spawn burst. Sometimes it triggers, sometimes it doesn't, and you can really build up a lot of dynamic elements into your effect by doing it that way. Okay, as I've said, next ones we're going to be looking at are the location modules, and we'll do that in the next videos. Okay, right, so in this next section we'll be having a look at the location modules. So 3 on the keyboard will camera shortcut you to this area. So far we looked at how to spawn particles, but we were just using a default sphere. Now we're going to have a look at more complicated locations and how we can control where the particle is added. So here in particle spawn, so as we're running the spawn script, it's going to create a particle. So the emitter update script spawns the particle, and then the particle spawns script says, now I've been spawned, where should I be? And we're going to use one of these location and positions to control that. Okay, if you're on one of the older versions of the engine, you may have individual modules for your locations as opposed to one big module that contains them all. So you might find this sphere location, box location, etc. That's obviously changed with the latest version, and now we just have one where you can select your shape from a drop down and the settings update. So just a slight change in workflow. But yeah, we're going to be looking at the initial one here. So shape location, sphere. Now, sphere is a very simple shape. It just has a radius. If this is bigger, we get a bigger sphere. If this is smaller, we get a smaller sphere. Very simple. But we can also control where our particles are spawned based on that shape, on that sphere shape. First thing is the distribution here. So we're doing a purely random distribution, and we can sort of blend between a fully volumetric sphere and a sort of shell surface sphere. So now we're purely on the surface distribution. There's no particles spawning inside, it's just a hollow object, and we can blend between those. So 0 is fully volume, 1 is fully kind of shell, and then halfway between the two, that's now kind of got a thickness. So it's a bit like a, I don't know, a hollow sphere, hollow shape, which can be quite nice, very nice way of working. We can also control our distribution based on our hemisphere. So if we want it just a half circle or a half sphere, we can do that. And we can do a quarter sphere, all this kind of shape, just defining areas and parts of that. And that's done through the UVs of the object. So a sphere is loaded in, it has one set of UVs going round, one set of UVs going top to bottom. And by using those values here, we can define where that's going to be. And so that's what the random distribution does. If we change that to direct, we'll give ourselves a bit more control. Default here, you can see U position and V position. So we're always spawning now on the V position of 0.5. So that's the kind of like middle circle, the widest point. We look at our sphere this way. And then our other value, our U value, where around, this in case has been driven by the emitter age. And if I just make my particle lifetime much smaller, you can see we get this kind of repeating looping ring. So as our emitter age goes up, our spawn location goes round, and then the length or the lifetime of the particle sort of controls the trail of the length of the trail. So just using purely the shape location here and then some properties from elsewhere in the emitter, we get this kind of circling looping animation. If we wanted to increase that, let's say we don't want to use exactly 0.5, we can control this with like a random value. 0 to 1 is going to go all the way around. If we did 0.4 to 0.6, that's just going to give us a little bit of thickness. And you can see how by having direct control, you can really affect where the particle's spawning. All based on the mesh sphere that's there and the UVs of it. Last setting here, sphere radius position, we can just sort of scale that radius. Just works as kind of a multiplier based on the sphere radius here. Third option, so random was anywhere, random, but with controls over which hemisphere and what have you, and whether it's surface or volume. Direct gives us direct access where we can set those values. Obviously we could do the same as random. If we just use random in both values, we're going to get random values. No problem with that. And the final one is uniform. So this is designed to work with a burst. If we look at the tooltip, it says only has meaning for particles spawned in a burst. And so rather than using a spawn rate, I've just added a quick spawn burst spawn value. And if I set my lifetime up a little bit longer, what this does is it spawns particles using the Fibonacci sequence, which is kind of cool. So it's saying, well, I know what my size is, I know what my spawn count is, I can work out the distribution of particles along my sphere in this kind of spiraling way to work out exactly so that each particle is as far away as possible from the other particles. And so you get this this sort of patterned uniform sphere, which is pretty cool. How much of the sphere do we want to cover? Same as before. Do we want it full or half hemisphere or whatever? And then how much do we want to spiral? And so depending on how many particles we have and how much distribution we want, the more we spiral, we'll get these kind of different patterns appearing. Very cool kind of Christmas ornament type effect, I guess. But with spiral set to 1, this is now particles sort of as equally distributed as possible along our sphere. Pretty cool. With all of the shape modules, there is a transform section or option. We can isolate it again with these top buttons if you wish. But we can change our scale. So let's say default non-uniform scale, let's make it taller in Z. And there we are, we've scaled it up. We can set rotation values and offset mode as well. So if we rotate and let's do a axis angle. So different ways of defining our rotation. The axis that we're pointing to and the spin. So in this case, let's do a non-uniform sphere in lots of ways. There we go. So the axis I want this to point towards, let's say, is Z. And now my x-axis here will be pointing towards my z-axis here. And I can control the spin around the other axes. Very nice. Easy to control rotations. If I did a pick your and roll, so I can just plug in rotation values. And you can do rotation axes that way, or rotation of a shape that way. We can do quaternions. We won't get into quaternions. They're another way of defining rotations that are quite complicated and almost certainly not necessary for most things. And we can plug in a transform matrix as well. Cool. Offset mode. We can offset our shape from where its position is. So currently our shape origin is the position. So that's going to be the position of the system. So basically our emitter origin. And we can offset in values. So I can move this. Now I'm moving it further away over here. So you can see that, maybe see that better here. So my system is here, but my shape has been offset. And so you can kind of move the shape before you sample it. As I say, these transform values will be common for all of the different shapes that we're doing, but yeah. So sphere defined by a radius, yep, makes sense, but then we can also scale it. Here we've created a very tall, long, thin, oblong, oblate spheroid, I believe would be the technical term, potentially. And then how we're going to sample our sphere and what we're going to do with that, well, we can just do a uniform, we can just do a random, and now we're just doing particles purely at random over the whole object or as a whole volume. And again, this will be very common to the different shapes that we're using. Or we can have direct access, and this is based on the object UVs. So one UV channel going around and one UV channel coming top to bottom. And then obviously the transform settings, etc. And the uniform Fibonacci spiral, which is quite cool. Okay, that's it for the sphere. We'll go through the other shapes in the next video. As I say, a lot of the settings will be pretty common for these. It just depends on what shape it is and what the input are for that. So we'll see that in the next time. Okay, so had a look at spheres. Let's do the next one on the list. That is cylinders. Now, cylinders, let me just reset this as well. There we are. A cylinder is a circle and a height. And so we have values for that. So we can adjust our height. If we set this to 0, we'll just get a purely flat disk. That's acceptable. If we have a small height and a very big radius, obviously we have a very big height and a very small radius. All these kinds of shapes are fine. And we can also adjust where the midpoint is. So if I turn the grid on up here, currently our midpoint of our cylinder is at the midpoint, 0.5. If I set that to 0, now it's at the bottom. Set it to 1, now it's at the top. And so you can control your cylinder that way rather than using an offset. Both would do the same end result, really. Okay. So let's do something like this. 150 radius, 500 height, tall, thin cylinder, tallish, thinnish cylinder. Now we have the same kind of distribution settings as before. So with the sphere, so we can just spawn on a particular hemisphere. that's the X side of our cylinder. So we've made kind of a cut in half cylinder. We can do the same in Y. That's cut in half the other way. If we enable both, we get a quarter. We can do a surface only band thickness. So this is the same as the slider in the sphere. This one doesn't have a slider, but does just go from 0 to 1. Confusingly, I think it goes the other way from 0 to 1. I just put that back into random. So here 1 is a shell and 0 is a volume. Whereas if I go to the cylinder, 0 is a surface and 1 is a volume. So that's the wrong way around, but there we are. That volume also appears to be pulling into the center. So we've got a non-uniform distribution here weighted around that. If we turn that off, now we have back to a uniform distribution. So some different settings for this. Use a curve to lathe the profile. Oh, that's exciting. So we can control the width of the cylinder all the way up. Interesting. Not really used this before, but if I set the key frames 0, 0, you can see we can control the uniform or the distribution of the particles along the cylinder as that goes from top to bottom. Very handy. If I change the tangents on this, well, I can do that way. You can make like a Christmas tree, all these kinds of things. Very cool. That's all the random distributions. And we obviously have direct one as well. So settings new and V, again based on the UVs of our cylinder. So 0 to 1 and 0 to 1. That doesn't appear to include the end caps, so they are handled separately. So if you're doing direct cylinder access, does it say this? No. The end caps would have to be added separately. Whereas if it's random, surface band set to 1, or sorry, set to 0, that does include the end caps. So depending on what you're doing, you may or may not want to do that. Cool. Very powerful. Lots of things we can do with our cylinder shape. Similar to sphere, different distributions, different randomness. That lathe profile, very cool way of controlling a volume. Obviously you can add multiple keyframes. It's just a curve. Really, oops, let's do that actually. Really control that and create some really cool kind of shapes. Okay, that's cylinder. In the next we'll have a look at box/plane. Okay, box or plane, well, another drop down to choose between box or plane. Plane is just a box with one of the values set to 0. Obviously we can do that manually just by setting the size to 0 ourselves, or we can use the plane default, which doesn't give us the option of a Z parameter. Either obviously is fine. And we just define our box by 3 values. So size in X, size in Y, size in Z, and then also the midpoint of those. So here 0.5, 0.5, 0.5, we're now centered around the origin. If I set that to 0s, we're now centered, or the bottom corner, bottom left back corner, is that right? Depends on the coordinate system, but that's now our sort of center point. So depends what we want to do. And then the only setting we have here for distribution, do we want to do surface band or not? So if I set that to 0, now it's purely around the surface of the cube, so hollow box. And if we set this to 0.5 or 1, 1 is now, this is now not a 0 to 1 normalized value, but rather a thickness in units. So I set a value of 10, 20, the bit tricky to see. So maybe make this much bigger. There we go. That's gonna be bigger than the actual shape. Make a box 500 units wide and a thickness of 100. You can see maybe a bit tricky, but now it's got a thickness, and where that thickness is we can do inside or outside or centered. So effectively we're defining the box itself and then defining a thickness, and that thickness is based in this case on a number of units. So in the dimensions now, total dimensions would be 500 units across for the box plus 100 units on each outside, so our total dimensions would be 700. And obviously we can change whether that is added on the outside, added on the inside, or added sort of centered on what we had here. So that would now be 500 plus 100. If that makes sense dimensionally. Cool, so we can make a box, we can make it hollow, we can make a plane. If it's purely a plane, it doesn't need any distribution, it's just a plane with an x and y value and a midpoint value. So very simple shapes to work with. In the next video, we'll have a look at the torus. Okay, so torus or donut, sometimes referred to as a donut if that's your preference, has two parameters. It is a ring around, and then it is also a kind of radius around that ring. So our large radius here defines the ring, the sort of disc size as it were, and then our handle radius defines sort of the thickness. So 50, 500 is not going to work, 50 is going to give it a bit more shape. So there's one value for this one and one value for that one. That makes sense. As with the other modules, there is some distribution setting. Distribution set surface to 1. Now it's a hollow donut, and you can see that at the sides here. Obviously that can be scaled in and out. And then U and V distribution, same as with the sphere. So you can say I only want particles on this half of my torus, or possibly on this part of my torus. And now we've created like a, I don't know, 180 degree half pipe bend. Very cool. We also have direct set, as always. Do we want particles everywhere? No, we don't. We just want to randomize it. So a random value between 0 and, or in this case, from 0.25 and 1, and in this case, from 0 to 0.5. So again, reading the UVs of the shape as it's been created allows us to define points on the surface, which is a very nice workflow. We also have torus knot. This is a kind of deformed torus with some noise, and you can set it to do, let me set that back to random, and we'll do full distribution. Oops, that's the other way around. And there we are. So we've got a torus knot. So two toruses kind of pushed together, and then some distortion added to it to create this kind of shape. We can control how many loops. Is interesting. And then how many ring loops as well. So we can create this kind of like almost a waveform pattern, adjusting the shape there. Pretty cool. And we've obviously got radius settings, large radius, small radius, and create some quite nice, interesting, maybe sort of semi-organic shapes. That's quite an interesting shape. As always, there is a slider for distribution between using it as a volume and using it as a surface, and also the UVs as well. So we can say, right, I only want to have half of the UVs. And there we are. Cool. And again, direct. So you can directly control where the particles are spawning. Moving on from torus, we have a ring or disc. Let me just reset this settings back to default. Choice of circle or hexagon. Circle will be purely round, controlled by a radius. Simple stuff. Hexagon will be defined by a number of shape, a number of sides. In this case, obviously 6. 6 is a hexagon. And so we get a kind of more mechanical type hard edge shape. And again, we get distribution across that. So thickness, and then in this case, it's distribution from the edges. And you can create these kinds of shapes as well. There we are. Cool. Last one, cone. Different types of cone: a spherical cone or a spherical wedge. Cone being a circle to a point, and wedge being a kind of square box to a point. And we have settings for length, angles, and what have you, if you want to create a cone type shape. That doesn't seem to work, does it? That's not what I want for a cone surface distribution. I'd want it to be on the cone part rather than the edge part, but there we are. Maybe spherical cone works better. No, it does the same thing. Okay, well, I wonder, does -1 work? No. Well, if you wanted that shape, you could make that shape in a different way, but there we are. That's the shape location. As I say, all of them have very common settings. So transform, how do we move and rotate and scale them? Distribution, almost all of them have that. Whether we have a full surface, or do we want a volume, kind of a volume-based shape, or do we want like a surface-based shape? Do we want parts of the shape? And you can do a lot with that. You can see, hopefully, from the types of shapes we've been making, you can do random things with toruses or torus knots. You can do kind of this lathed cylinder. So there's a lot of control just within this one shape location module of how we build these things up. And we can also stack them. So a very common thing to do. In this case, let's make it nice and obvious, shall we? Yeah, so we'll just have a sphere, and I'll add a new shape. In this case, I will add a box. And what it's doing is it's kind of the uniform of, or the Boolean unison of these two things. And so, maybe if I quickly find some space, load up my pen. If we draw we have shapes, we draw a box, and we draw a sphere, or at least a circle. These are our two shape modules, and our particle can spawn anywhere within this one and anywhere with this one. But because we've nested the two modules on top of each other, effectively what happens is the particle spawns, say, here inside my box, and then it uses that position as the center of the next shape module. And so we get another circle. That's not quite in the right place, but hopefully you see the idea. So the possibility space, if you take a cube and a sphere and add them together, you would get a shape that would be basically like this, a kind of curved box. Not drawing this the neatest thing in the world, but if you look, this corner here could have a circle on it, and so all of these things are within it. This point here is also within. This point here is. This point here is. That's terrible drawing, but basically every single point inside this cube could also have this sphere applied to it, and so you get this outer kind of edge to your possibility space of kind of like a rounded rectangle or a rounded cube volume. Maybe not the clearest example, but hopefully that makes sense. Each time you're adding a new shape module, you're using the previous calculation as your origin for your next shape module. And so you can nest these things and you could really build some very powerful things. If we think about that sort of lathed cylinder, creating this kind of, I don't know, onion turnip type shape. If we wanted some thickness to it, we could add a disc. I mean, that's kind of what you could already do with the thing anyway. But you could maybe add a cone. I don't know. Maybe the disc is at an angle. And now the whole shape is kind of combining together, and you're creating this really kind of unusual volume. Maybe we use a torus. So that would be like the torus knot here, and every part of that point, and so on. So there's a lot that can be done with just the simple shape modules. Either by just using their settings inbuilt in the distribution, or by combining them together. And if I actually up my spawn rate, my spawn burst, unfortunately, as in the current Unreal, there's no way to really visualize these shapes. There used to be an option, a checkbox to sort of show that visualization, but currently not available. I think it's coming back in future versions, hopefully, so we'll be able to see the shapes we're dealing with. But as a shortcut, you can always just spawn a large amount of particles. If I make this GPU sim so it can cope with lots of particles a lot easier, we'll make these much smaller. Something like that. You can see by combining our sphere, which is very accurately this shape, and our box, which is this shape, we get a kind of rounded edged box. And there's a higher distribution in the center because you're more likely to get a particle in the center than you are around the edges. So very powerful system for combining things together here. Maybe that shows it better. So if I put my sphere radius to 0, obviously I'm only getting my box, and you can see all my particles. Whereas if I now add some radius, they're now kind of like blurring that edges, which is quite a nice way of working. Okay, that's a lot of shape module. There's a lot of options in the shape module. Select your shape, select your sort of primitive parameters, so radius, edges, half width, that kind of thing, and then set your distribution as well, so full volume, full surface, and so on, or based on the UVs directly. So very cool. All right, moving on. In the next module, or in the next video, we'll have a look at the next module, which is the grid location, which we mentioned before, and we'll look into in a bit more detail in the next video. Okay, right, so moving on from the shape location, awful lot we can do with that. We've seen that, combine them together, add them, nest them, edit settings, all you want to do. We're going to move to grid location. So we mentioned this before, because the grid location module requires a spawn particles in grid module. So if you enable either one of them, it will give you an error, little red dot, saying that the other one needs to be enabled. As long as they're both on, they work together in harmony. And we're just defining a grid. We're defining an X, Y, and Z value. How many particles should we spawn in those axes? And if I just set this to be 1 in X, now we've got a 2D grid. Now, unfortunately, this is slightly off-centered from the grid. If we wanted this to be centered there, we need to use the grid location module. So the spawn particles in grid defines our sort of step size, how many in X, how many in Y, and it's just like a spawn burst, so it has a spawn time, etc. And then our grid location defines what the grid is doing. So in this case, we have padding. Even though I've set it to 1, I might want to turn my padding off in X, and now that's aligned with the grid there. But we can adjust the spacing between our grid cells, whatever we want to do. We can offset it. So if I offset by 5, it's now moved across that way. I see. So this is how many units we want. Either we can offset in Unreal units, so 500, or what would it be? It would be, well, I can do the calculation, 15 times 5, yeah. So 75 units would move that across the edge, or if we normalize them, we're now talking in number of grid cells. So 1, 2, 3, 4, 5 grid cells. We can add some jitter and some randomization. Do we want to have our cells directly on the grid point, or do we want to have a little bit of a breakdown? Now this is a really handy way of doing a sort of semi-uniform distribution. Theoretically, if we randomize values within the square, it's possible for all of the particles to be in the bottom corner. It's not very likely, but it's definitely possible. Whereas if we do a perfect grid first and then add a little bit of offset, we know we're going to be close to a perfect grid or close to a uniform distribution. So that's quite a nice way of conforming or controlling your particles so that you don't ever have that unlikely scenario of a really empty area or a really empty corner. So that's about it for a grid location. You can obviously do a volume. If we do 10 by 10 by 10. We add another, and the padding as well. So we can add a sort of volume of particles. And there's some limited uses for this. Either a sort of more uniform distribution within a cube, as I just mentioned, using that jitter. And we can obviously jitter a little smaller amount if we wanted, or we could have a random amount of jitter, random vector thing 0 and 1. And so we're like mostly, whoops, 0.5, not 5. So it's mostly a sort of grid aligned particles, and then occasionally, or they're a little bit offset, some of them are a little bit offset, and so on. But yeah, useful for a few things. Yeah, if we're filling a volume or filling a shape and you want it to be not random but rather a bit more controlled, we could use a grid. Or if you're doing something where, let's say we're spawning a particle, or we're reading from a texture, and we want a particle kind of per pixel, and we'll cover that as an idea later when we look at texture sampling. Yeah. Okay, that's the grid settings. As I say, the two need to work together. If you've got one on and not the other, it will give you a warning. And it's basically controlling how many particles are we spawning in that grid, and then what are the dimensions of that grid, what's the spacing between the particles, is there any randomization, and have they been offset, and that kind of thing. So yeah, grid spawn. Next we'll have a look at a quick jitter. Okay, so the jitter position module. Well, if I go back to my grid and I turn off the randomization, jitter position will basically do the same thing. So it'll take the position where I am and just jitter, jitter being a technical term for a little kind of movement, and it will just say, right, move this far and this direction. And so in the offset we're doing a random amount, and the jitter amount we're doing 5, so we're moving a little bit in every direction, and you can see it's breaking up that uniformity. If I just go back to a single layer, it makes it a bit easier to see. We are jittering in every direction because we're using a random value. If I change my jitter offset, if I set this to be a new local value, and I'm only going to jitter in X, let's do Y, shall we? Jitter amount. Okay, well, they're all jittering the same amount, so we need to randomize something. And let's do a random value between 0 and 5, or 0 and 10 maybe. And you can see here they're moving across, and we can create this kind of like almost computer readout type display, where there's little points. They're all spawning in the grid, and now we're jittering them and offsetting them. So this is already built into the grid location module basically. So we could do the same thing here, jitter, and we'll do a value of 0 to 5 in, it was Y, wasn't it? 0 to 1 in Y, and there we go. So the same result. So very common when you've got something spawned in a uniform amount, we want to just break up that a little bit. We could just use a either inbuilt jitter, such as in the grid module, or we could use a jitter position thing ourselves. We can do a delay, and we can do timing, and we can have jitters that happen as part of our loop. That doesn't seem to be doing anything. Oh, I see why. Jitter delay works in update. That's right. And so now every 0.2, it's now doing a jitter, and you can get this kind of like offsetting randomness. If we do random plus and minus, they're gonna. So generally, when we're dealing with position modules, they're going to be in spawn because that's when we care about them. In this case, jitter has a little animation component, so we can do that in update, and it will do that for us. I have said here, jitter position works in update. We'll probably make my own. What do I mean by make my own? Well, we don't need to do everything via module. We can just take data and directly manipulate it. And so I have here a set position. Let's just make a new one from scratch to show how this works. So if we do set new or existing parameter directly, So we can use this to create parameters, create new parameters. We can use it to edit existing parameters. It's just a sort of very quick way of working with our own set of data. And if I add, so position, so particle position, that's one of the parameters that we have access to here in our stack. And then rather than using this, I'm going to change this to be a add vector to position. The position I want to use is the existing particle's position. Particle position. And what do I want to add? Well, in this case, it's going to be a random vector, random range vector. And I'm going to add between 0 and 5 in y. And you can see we're getting that same thing, that same effect. So basically the same module, basically doing the exact same calculation. In this case, let's do 10 minus 10, just to make it the same. The only reason I would do this myself, I mean, I didn't realize jitter position existed just because it's so easy to add that randomness yourself. But hopefully it just demonstrates a key point. Everything in Niagara, although we're going through the existing modules and we're going through them step by step, and there's an awful lot of powerful data and things we can do to that, we can also just roll our own. We can also say, right, well, actually, I want to add a small amount of random value. I can just do that. Take position, add a random value, got the result. I don't need to make my own module for it, or I don't need to search around to find a module to see if it exists. Obviously, if it does and you want to use it, not a problem. But personally, something like this, that's quite a sort of simple thing to add, I would just go in and sort of add myself. And we might want to rename this. If I call this get a position directly. There we go. And so you can always kind of go in, do a set particles module, or set new and existing directly, and then just give it a name. And it will give you this italics name to show you that that's just a name, not a module name, if that makes sense. But there you are. Yeah, the jitter module just slightly moves things around. Useful. Yeah. Also, we can just make our own very, very quickly. That does that for us. Personally, this now I know exactly what this does. This module is inherited. If someone makes a change to the source code, I inherit that source change. Maybe I don't want to do that. Yeah, I mean, it doesn't really matter. At the end of the day, the results are the same. But whether you're working with your own modules that you've quickly made, or whether you're working with modules from the library, yeah, it doesn't matter. It does the same result at the end of the day. So, yeah, jittering. Just a little offset. When you've got a uniform distribution and you want to make it less uniform, have a little randomness in it, we can do that with jitter. Very useful with this grid, but also equally would be useful with the uniform distributions on the sphere, that kind of thing, just to create a little bit of random movement. And all it's doing is adding a random value to our current position. Cool. All right. In the next module, we'll have a look at some of the other position and location modules. Okay, right, so the next one we're going to have a look at here is the system location module. Now what this does is it will get the location of where the system is, so where the actual actor is, and it will put the particle there. So it effectively does nothing. If we don't have a module enabled, any location modules, the default position for particles will sort of fall back to is the system location. So I don't really see why you'd ever need to use a system location module. Again, we have an offset here. We could do a random shape. So if I do a random vector, let's say some size between plus or minus 10, well, I've basically defined a cube. So now I've got a shape module, effectively a box shape module here. But it's not really doing anything that any of the other modules wouldn't be doing better. So probably a legacy thing, it's probably hangover from the early days of Niagara where the system location wasn't the fallback. But yeah, I can't see any reason why you'd use the system location. If we disable that for a second, do another set new or existing directly. Let's put it in here. You can always access the system location as a parameter. If I were to do, let's say, particles position, that's what I want to set. So I'm going to make a new input for particle position. It even defaults to that simulation position. So this is doing the same thing as this is, obviously without the randomness adding to it. So the data that this is providing you is always accessible via the sort of the parameter system. So I'm not entirely sure. Like I say, it's probably a legacy thing, but that's the system location. Doesn't seem to do anything that I would deem useful, or at least not something that you couldn't do a different way that would be more powerful, easy to understand, more features, have more features to you available to you. So included it for the sake of including it. When you go down the list here, if you put in location, obviously it comes up, but I can't really see any reason why you'd ever use it personally. So there we are. Okay, last two we're going to look at are the static and skeletal mesh location modules, and we'll have a look at those in the next video. Okay, right, so the last two location modules we're going to be looking at here are the static mesh location and skeletal mesh location modules. We just start with the fresh one, static mesh location. And first thing we get is a warning. If we're using a mesh location module, we need to use a mesh. Now this is a very complicated module, there's a lot going on, so we'll go through most of the settings. But yeah, there's definitely a lot you can do with this. So firstly, yes, assign a mesh. So how are we going to do that? Well, if we just put something here in the preview mesh, and we're going to use the preview matte sphere, this will now appear here. You'll see we're sampling the mesh location, and it's reading the particles. Now, if we open up this mesh, there is a setting that is required, which is called allow CPU access. If I turn this off, go back to my module here, it's still working, but there's an error. So we need to click the fix now button. So CPU access error. So there's a setting in the static mesh itself to allow CPU access, and that allows it to then be sampled as a static mesh in Niagara. Easy to fix, click the fix button, but that's exactly what it's doing. And yeah, it's sampling the mesh. How are we sampling it? Well, currently we're sampling the triangles. If you look, there are some areas of higher density. Well, if we open up the model and look at the wireframe, they are the areas of higher density. And so when you're sampling a mesh, it might be that you want to make a kind of uniform distribution density mesh to allow yourself to sample a bit more uniformly. There is an option for this as well, support uniformly distributed sampling, support GPU uniformly distributed sampling. And so there is a more expensive options for you there. If we do that, we now should be able to do so now it's automatically done it. There we are. So now our mesh is just sampling, or our module is now sampling our mesh, and it's uniformly distributing the triangles. So there's an additional cost to that. So it's up to you whether you want to use a mesh that has the correct distribution for you as a sort of separate mesh. Obviously, you can always make that invisible, that kind of thing. That was the old workflow. Nowadays, you can just turn on these settings here, support uniform distributed sampling, or support GPU uniform distributed sampling. Additional memory cost of 8 bytes per triangle. Well, there we go. So we'll turn that off for now. Now we'll go back to our non-uniform sample. And what we're doing here is sampling triangles, like I said. You can sample specific triangles. This is now sampling triangle 0. If I sample triangle 50, that's down here. It's not very useful. We might want to do a range. But even with a range, we are sampling areas of our mesh, but the distribution of numbers within our triangle, it probably needs to be built in a very specific way. So this mesh obviously wasn't built with that in mind, and so the various patches, there's some cohesion to it, but it's not like you could kind of mask out a certain area. But it is available if you do that in the right way. We also have this one here, section filter. Well, the section filter area is up here, and we could say let's use material slots. So this model has 2 material slots on it. If I close this, material 1 or material 0 and material 1. So that's either the sort of grey shininess, or in this case it's just set to the world grid, and that's the sort of other parts of the sphere. So if we wanted just to spawn on a particular one of those, we can do so. We can use the allowable material slots. Interestingly, it doesn't seem like I can get it to do no particles. So I can swap. And I should be able to do all particles. Well, it's definitely doing something. Not sure it's exactly doing what I would expect. Index 0, 1, index 1, 1. Unless there's another index in here that we're not seeing. Nope. Try direct section filter, triangles. Yeah, random section filter, that should use this area here. And it does seem to be, but not completely as I would expect. So there might be a little bug with that. It might be because the world grid material is not set correctly. Not entirely sure, but you can see it's definitely having an effect. So that is now only sampling the outer material. If I do that, that's also sampling the inner materials, that's sampling both. And that's sampling just the inner. But the sort of 1 and 0 seem to be inverted, depending on which index it is. So your mileage may vary. That seems like it might be a bit of a bug with the engine. But that should work when you're on section filter to use the different material slots. But there we are. So different ways we can sample. Sample triangles or vertices. We can sample a random amount, or using a filter via sort of the material slots, or we can go kind of direct to the vert numbers as well. Okay, that's different ways we can, sort of different models we can sample, different ways we can sample it. We can also use this module in a few different ways, and that's this source mode up here. So default kind of picks the best one for the position you're in, but these are the three options you really have. Default mesh only. Well, if we set the mesh in here, preview matte sphere, it's always going to be this model, never anything else. It's not dynamic in any way. Sometimes that's what we want, that's fine. If we want though, we can set it to either attach parent or source, and both of these are kind of like a slightly smarter way of doing things. So if I set this to attach parent, what that's going to do now, if I compile this and go into the world, if I just create a quick cube mesh, what I can do is I can take my particle system here, and if I just right click, there's an attach to, and I'll use the little eyedropper and just attach it to the cube. Now if I hit spacebar or whatever your reset particles keyboard is, command is, you'll see it's now inherited the mesh from the static mesh actor to use here because it's attached in the world. Very powerful way of working, means we can just sort of create one system that works for all meshes and then attach it to different meshes, and it'll update and kind of like populate its own data correctly. Very useful for sort of character attachments, that kind of thing as well. If I detach it, right click detach and then reset again, now I'm back here and it doesn't have the setting in it. So very, very useful. We can also do this via user parameter. So I've got one here, let's just delete it. In our static mesh location, this whole area, this whole input is just an input. We can make a user parameter about it. And now rather than having the settings here in the system, they're available on the actor in the world. But what we can do with that, if I set this to source mode, source actor, and we can again just highlight and pick. So we're either doing it via an attachment, it'll automatically pick up what it's attached to, or we can just say this is the actor that we want to spawn our particles, or we want to sample to spawn our particles, and that's sort of the source mode of doing it. So I'll just go over that again. In here, the static mesh input, if it's set to attach parent, it will just pick up what it's attached to. If it's promoted to a user parameter, and this is of type Niagara data interface static mesh. So we could just create one, data interface static mesh. There we are. That would be the data type. Let's create a second one. It's a bit off screen, you can't see it. There we go. So that's created another one of these. So whether we create it manually or we promote it, once we've got it, we can just drag and drop and we can replace this input. And now this is a user parameter based static mesh input or data interface, and we can select source, select what actor to spawn our particles from. And now they'll be spawning. Well, it doesn't like the BP because it's a blueprint rather than the static mesh. So we've got to make sure we're selecting the right actor type. But if we create another static mesh cylinder here, I can just click and pop. Now I'm sort of targeting which of my meshes I want to be sampling for my static mesh sample module. Okay, hopefully that makes sense. Quite a powerful thing to do. Yeah, so what are we doing here? Well, we've sampled our mesh. We can sample it via triangles or vertices. We can turn on uniform sampling. We need to have the fixed CPU error. But once we've sampled, what are we sampling and what are we doing with it? And that's what the imply section here is. Now, we haven't covered this yet, but there is a great little option up here in the three little lines option menu. We can show parameter reads and show parameter writes. So I'm just going to turn them both on. And what this does is it adds a section here at the bottom to every module, and it tells you what the data is that's being pulled in by the module and what's the data that's being written by the module. So if we go to something like the spawn burst, it's picking up time, how long since the last time has changed, loop count, looped age, all of these things. It needs to know these to be able to do what it's doing. And then it spawns out, or spits out, I should say, various other bits of data based on what it's programmed to do. So in this case, the spawn burst value, has spawned this frame value. These are written by this module. So let's have a look at the static mesh location module. This is sampling or bringing in particle position, mesh orientation, these kinds of things. But what's interesting is what it's writing. So there are 6 values here, or 6 items of data that are being sampled from our mesh. Position, well, we're seeing position, that's already being applied, but we're also getting the normals, the rotation, the UV, so the UV coordinate of where that sort of sample happens, the velocity if it's moving, and also the vertex color. Now these are obviously a lot of data, lots of really interesting things here, and some of it's being applied directly. So here in the apply tab, the position sampling is set to apply, and so that value is now automatically being applied to the particle's position. And you look at the tooltip, it'll tell you what it's doing. If we set this to output, it's now taking that value, sampling it, still exists. If I go to parameters and I go over here to the particle attributes, there will be a particle static mesh location output position or sampled position, but it's not being applied to our particles yet. And so we could do that with a set new or existing. If I set my particle position, and let's use my sampled position, and there we go. So that's doing the same thing. So inbuilt into the module is this sort of apply section where we can set our data directly into our parameters, or we can just not do that and we can get the data ourselves. So it allows us to use the static mesh location module to do sampling without applying. It doesn't have to be a location, you can just sample. I believe in previous versions of the engine there were just static mesh sample modules, but I don't think that exists anymore. At least I can't find it. Yeah, just static mesh location. But that's what's happening. That's what this output is doing. It's taking the value from the mesh and then it's applying it to the particle directly. We can do that ourselves, or we can use the module to do that. We do have this option of rigid or soft. So if it's moving, if the object is moving, you can apply a scale factor to it. And so you can kind of sample a mesh as it's moving and updating, and then your particles will kind of trail behind. Never really used it myself, but you can set the scale here. Cool. So what else are we getting? Well, we're getting velocity. Again, we're not using that on the particle's velocity, but we could do. We're getting orientation. So if these were aligned meshes, they would pick up that orientation. And we're getting vertex colors as well. So we can use vertex colors similar to the sampling we saw here, where we use the material slots, we can actually use vertex colors to do sampling as well, and we'll have a look at that later on. Okay, quite a powerful module. There's a lot going on. Let me just reset this for a second. Core thing, how you'll be using it, whether it's source, attached parent, or default mesh only, depends on which we set. If we want to just use that one, the default will pick whichever is correct, or whichever is most likely to be correct, depending on your setup. So up to you how you want to use this. But if we are going to use a mesh, we want to have the mesh set to have CPU access available. Let's do preview, isn't it? Preview material sphere. So make sure that when you've got this, we have CPU access available. And if we do want to have that uniform distribution, there's an additional setting here with an associated cost. Different filters for our material, not entirely sure that was working. And then we can sample either triangles or verts and then choose whether we're applying or not applying that data, whether we're sampling it or just saving it. And the last thing, parameter reads and parameter writes. I have these on all the time. It's really useful to be able to debug, going in, see what your module is actually reading, what it's actually writing, what data do you get. So yeah, worth checking out whenever you're using a new module, what the reads and writes are. Okay, we will cover some more with sampling later on, but for now we're going to move on to the skeletal mesh location and see how the difference works with the static and skeletal mesh, and we'll do that in the next video. Okay, right, so in this last one we're going to have a look at skeletal mesh location. Again, we're not going to go too deep into everything. There's an awful lot of settings and things we can do here, but broadly the workflow is the same. So source mode, we have 2 options now rather than 3. You can't just tell it to use the preview mesh. Instead, we can have source mode, allowing us to use a parameter and select from an actor in the world, or attachment, and then it will attach and automatically use the parent. So the preview mesh here, this is only going to give us an example here, although actually it's also going to show us in the world as well. So preview mesh, I guess if you don't set either of the others, it falls back to using the preview mesh, which is a bit confusing potentially, since that maybe should be an option in here, but there we are. Apart from that, it's the same kind of settings as before. Obviously skeletal meshes are more complicated than static meshes, so there's more options in terms of filtering. So we could do things by component tags, sampling regions. Now sampling regions, if we open up our mannequin, open up our skeletal mesh, we have in the asset details here in the skeletal mesh editor something called a sampling region. And so we can define a region here. If I just do this from scratch, we'll start by setting a sampling region, give it a name, particle sample, and then we can either use material filter or bone filter. So what do we want to sample from? In this case, let's do materials, and this object has 2 materials, and we'll use the chest logo. So I just want to spawn particles from the Unreal logo here. That's maybe a little bit difficult to see. Okay, now I've set up my sampling region. I could do that again on materials or on bones or however that wants to be. If I go back to my Niagara module, if I add a sampling region, this will now appear, particle sample, and I need to tell the sampling mode not to use all triangles, but instead to use sampling regions. And what we should find, although there are many particles, let's maybe put this number down to something a bit more reasonable. I don't know, maybe 50. Let's make them much smaller. You can see we're sampling that region. Now, the U shape obviously is coming from the texture, and so to get the information from that is a slightly more complicated thing. So it's sampling the region, including the alpha. So here it looks like it's the just sort of limited to that shape. If I turn on wireframe, you can see we're getting the whole patch. So there is still some limitation with this. We'll look at some workarounds for that kind of thing later on, but you can see we're able to specify areas of our mesh using these tools. Okay, apart from that, there were obviously other obviously other options. If I just turn the sampling region off for a second, we can sample triangles and verts like we did before. We can also sample bones. And if I zoom out a little bit, maybe make the particles a bit bigger, we can see we're now sampling our bones, and that's where our bone sampling region would have been applied. And we can also sample specific bones, direct filtered bones, this kind of thing. Bones and sockets, bones and sockets, triangles and vertices. So depending on what we're doing, we can sample different things depending on what we need. As with the skeletal mesh, as with the static mesh sampling, we have the option to apply it or not. Looking at the list, we are getting velocity, scale, rotation, position, bone index, position without offset. So depending on what we're sampling, we're actually getting different data here. So we're getting some bone output data. If I set this back to triangle, now we'll get the same as we saw before. So the normal, the EV, the velocity, vertex, color, etc. So the outputs here changing depending on what we're sampling. Okay, let's do random all triangles. There we go. That brings the whole thing back. Something like that. Let me see the whole mesh. Okay, so as I say, same kind of workflow. Bring in the mesh. I don't think CPU access is required for. Oh no, yes it is. So enable CPU access. That will probably be again a warning that Niagara will tell you, or possibly not. Yes, there we go. Fix now. The fix now errors, when they appear, you just click them, and so it's easy. It's so easy to forget when they come up and when they don't. But yes, apply your mesh. Fix now on the CPU access to give the CPU access to the model. Set up any sampling regions. Set up all your sampling and filtering as required, and then take the data and do with it what you wish. So either apply the data or just output the data and use it later on, and then we can go on and build up our effects from there. I will say often it's very simple, or often it's a lot easier to use a sort of sub mesh. So if we had kind of like a character, we could set up the materials and the sampling regions and really go that route. Or let's say we want to just sample a piece of the armor or the U shape, we could instead also just make a separate mesh, import the U as its own piece, and do it that way. And sometimes it's a lot simpler to kind of use an imported mesh that never gets rendered anywhere else as our sort of sampled mesh, and do it that way instead. So there we are. We will go into more information using these sampled bits of data later on when we get to some of the more advanced techniques. But for now, I think we'll leave it there. The most important thing, well, what we're talking about now is we're talking about locations, and this is definitely giving us the location of the mesh as we went. So, quick overview. We've done a lot. Shape location does almost everything. Lots of different primitives, lots of settings, whether they're hollow or volume, size, scale, distribution, all of that kind of thing, all within the shape module. You can stack multiple shape modules, and that works as a kind of additive to the possibility space, if that makes sense. So you're kind of stacking one position, randomizing, stacking that next position, randomizing. And so you can do some quite intricate shapes like that. Or of course we can control things directly. So we could use a grid, a nice uniform distribution, and then have a bit of jitter. We can make our own jitter. It's quite a simple thing, just a random value added to position, but yeah, there's a module for it if that works, or you can make your own, no problem. And we can always set this data directly and so on. Finally, static mesh and skeletal mesh locations. Very powerful way of accessing non-primitive shapes, I guess. If you want something that's really sort of specific shape, really complex, you can just model it and then import it and then sample it. It will be more expensive, both of these modules. Well, static meshes are more expensive than shapes, and skeletal meshes are more expensive than static meshes, but that doesn't mean it's not something we can be using. It's not so expensive that it's not for real time or anything like that. Okay, lots of information there. We will use these again later on in our worked examples, depending on what it is we're making. But for now, we're going to leave the location modules and move on to the next section, which I believe is vectors and velocity. But we'll do that obviously in the next video.